Satellites do not have a data problem. They have a delivery problem. Every day, they collect images of storms, shipping lanes, crops, oceans, and critical infrastructure. But in some remote sensing systems, less than 10% of that information makes it back to Earth, because the sensors can generate data far faster than satellites can transmit it through limited ground station windows. And when the information finally arrives, it may already be too late. A storm has changed direction. A ship has left the area. A damaged power line has already triggered a wider failure. China's proposed solution is to stop treating satellites as passive cameras. Instead of sending every raw image to the ground, the satellite would analyze the data in orbit, discard what is irrelevant, and transmit only the result. Wang Shangguang, the founder and chief scientist of the Tiansuan Constellation, compared the change to turning a satellite from a pager into a smartphone. Wang Jianyu, a senior scientist involved in Shanghai's space computing effort, was more direct. Onboard computing, he argued, is no longer optional. It is infrastructure. On July 18, 2026, Shanghai Xingshu Tiansuan presented this idea to the international market through the first constellation of its proposed 1,000-satellite Xingshu plan. The project was described as a step toward China's first commercial space-based computing network. But that description creates a misleading image, because what Shanghai is building is not simply a conventional data center placed above Earth. That raises an obvious question. If China is already building computing networks in orbit, have the United States or Europe reached the same point, or are all sides using the same futuristic label to describe very different technologies? So what is a data center in space, if it is not simply AWS placed in orbit? For now, it is something much narrower. A satellite collects information, processes it beside the sensor, removes what has little value, and sends only the useful result back to Earth. Instead of downloading thousands of raw images of an ocean, for example, it might return a single alert identifying a ship that has changed course. That model is usually called edge computing, and China had been testing it long before Shanghai announced the Xingshu plan. A system deployed through Beijing University of Posts and Telecommunications Tiansuan Constellation reported a 50% improvement in inference accuracy while reducing transmitted data by 90%. The results supported a straightforward argument. When the connection is limited, it can be more efficient to move the computation to the data than to move all the data to the computation. There was, however, a problem with describing Xingshu as China's first space-based computing network. In May 2025, more than a year before Xingshu's public unveiling, ADA Space and Zhejiang Lab had already sent 12 computing satellites into orbit under the Star Compute and Three-Body programs. Together, the batch was described as providing 5 POPs of computing capacity, with onboard storage and laser links designed to let the satellites exchange information without routing every task through Earth. BUPT had also spent years testing its own system and reported 8 experimental satellites by July 2026. China's orbital computing effort is therefore not one program following a single national roadmap. Tiansuan began as an open research platform. Three-Body demonstrated a larger launched cluster. Xingshu is Shanghai's attempt to turn similar capabilities into a standardized commercial and industrial network, while a separate Shanghai project is pursuing optical computing in orbit. Even the project's supporters draw a boundary around the claim. The objective is not to replace terrestrial data centers, but to handle workloads in which bandwidth is scarce, response time is critical, or ground coverage is unavailable. The idea is less cinematic than an orbital version of the cloud, but technically more plausible. Satellites are becoming capable of processing the information they collect. The harder question is whether the infrastructure around them can support that shift at scale. A satellite may be able to observe an entire ocean, but the connection back to Earth is still relatively narrow. Traditional systems collect large volumes of raw information, wait until a ground station becomes available, and then begin transmitting it downward. The problem is that some data has a short, useful life. A storm image delivered after the forecast window has closed is no longer an early warning. It is a historical record. Processing information in orbit can reduce that delay, but it does not remove the larger constraints surrounding the system. The strongest case for orbital computing is still selective. Identify a wildfire, detect a ship changing course, or isolate the small part of an image that requires immediate attention. The claim becomes more difficult when that model is expanded into full-scale data centers operating above Earth. The first barrier is cost. AWS Chief Executive Matt Garman argued that orbital data centers remain pretty far from reality because launch capacity is limited and placing hardware in space is still extremely expensive. The second barrier is survival. Conventional processors are vulnerable to radiation, failed components cannot be replaced easily, and vacuum does not make cooling automatic. Heat can only leave through radiation, which means a large computing system would require equally large thermal control hardware. Then there is power. Solar energy is abundant in orbit, but supplying a data center at industrial scale could require extensive arrays, additional launch mass, and an architecture that has not yet been demonstrated economically. Xingshu's own roadmap reflects this gap between ambition and current capability. The project is promoted as a future network of 1,000 satellites, yet its verified status remains an engineering validation program that must pass through several deployment stages before commercial operation becomes possible. And because Xingshu itself is too new to provide meaningful financial results, the nearest comparison is ADA Space. Its revenue increased as its satellite business expanded, while its net loss widened to 255.9 million yuan in 2025, and its gross margin fell to 20.4%. The technology may solve a real communications problem. That does not mean it can solve it cheaply. But profitability may not be the only measure Shanghai is using, because behind the satellite network sits a much larger industrial and strategic project. This is where the story changes. Xingshu is not being built like a conventional startup, because the company at the center of Shanghai's announcement was incorporated only on May 8, 2026, with registered capital of 30 million yuan. Roughly 10 weeks later, it was presented as the operator of a future 1,000 satellite computing network. That does not mean the project appeared from nowhere. It means Xingshu is the public-facing layer of a much larger system. Its controlling shareholder, Zuntian Qianhe, had recently been acquired by Drinda, a listed company best known for manufacturing photovoltaic cells. In its own filings, Drinda described the acquisition as its formal entry into commercial satellites, and said it intended to explore computing power satellites alongside space-based solar technology. The unlikely connection begins to make sense when the full architecture is considered. Orbital computing requires energy, spacecraft, communications links, onboard processors, ground infrastructure, and customers. Drinda and its partners are not simply trying to build a satellite, they are attempting to connect each part of that chain. Xingshu, in other words, is less a standalone space company than the organizing label for an industrial coalition. Shanghai officials have described the plan as a platform that could attract more than 100 supporting companies and eventually generate over 100 billion yuan in related annual industrial output. That figure is a projection for the broader ecosystem, not revenue already earned by Xingshu, but it reveals how the city is measuring the project, not only through satellite sales, but through factories, suppliers, research programs, and technical standards. And Shanghai is not working in an empty field. BUPT tested orbital computing through Tiansuan. Zhejiang Lab and ADA Space launched the Three-Body cluster. Shanghai is now trying to convert similar capabilities into an integrated commercial network, while also supporting a separate optical computing satellite program. So the competition is not simply China against the United States. Chinese cities, laboratories, and companies are also competing with one another to define how space-based computing will work. That matters because artificial intelligence is increasingly constrained by power, cooling, data movement, and infrastructure ownership. China has already placed gigawatt-class space computing within its medium-term planning language, while American companies are examining many of the same possibilities. Once computing becomes infrastructure, it also becomes geopolitical. The real question is no longer whether one satellite can process an image in orbit. It is who will control the networks, standards, energy systems, and supply chains that determine where the next generation of data is processed. So, is orbital computing a real breakthrough or an expensive illusion? At the moment, it is partly both. The technology itself is becoming credible. Satellites can already filter images, run limited inference, and return useful conclusions without transmitting every piece of raw data to Earth. For weather monitoring, disaster response, maritime tracking, and other time-sensitive systems, that may be enough to justify the additional cost. What remains unproven is the larger promise that space will soon become the cheapest place to run artificial intelligence at data center scale. Reaching that point would still require cheaper launches, reliable space-grade processors, industrial power systems, high-capacity optical networks, and a practical way to remove enormous amounts of heat. Shanghai's own position is more restrained than the headline suggests. The purpose is not to replace terrestrial cloud infrastructure, but to process selected workloads where delay, limited connectivity, resilience, or control matters more than price alone. That distinction is important because the value of infrastructure is not always measured by whether it is the cheapest option. A satellite that identifies a wildfire before its next contact with a ground station may be worth more than the cost of the computation. The same may be true for a damaged power line, a ship changing course, or information that a government does not want routed through vulnerable terrestrial networks. This is why Xingshu can remain commercially uncertain while still being strategically significant. Its immediate market may be narrow, but the institutions behind it are building the energy systems, communications links, standards, and industrial capacity that could make wider orbital computing possible later. The likely future is therefore not an entire version of the cloud floating above Earth, nor is it a return to satellites that simply collect data and wait for instructions from below. It is a middle layer, machines in orbit that decide which information matters before that information ever reaches the ground. And if that model works, the most valuable part of the network may not be the computing power itself. It may be the ability to act first.